Hello, everyone. This is Professor Ma, and this is the short introduction on the sections Auckland parameters and curvatures. Uh, when we have a graph, a curve, a y graph of x graph, want to parameterize in terms of t. That is, we want to describe a point moving along the curve according to times, and there infinite many way to do it because people drive different speed along a different curve. You can drive in any manner you want to, and you can start at different starting points. So here are two different parameterization of exactly the same thing. That is a line in the same direction, 3, 4, but they have different two parameterizations of the points sitting on the same line. So this is a justification, basically saying that, oh, because the line must be parallel first, and then they pass into the same point, hence they must be the same line. So those two different ways of parameterizing the line. And then we also have, under some condition, we have this arc-length formula, provided the curve doesn't, if the parameterization doesn't double back on the curve, then we can use this as the arc-length calculated from time A to B, the distance the point travels. So the arc length of the first curve, C of t, is 5, the length of this. And between time 0 to A, then it travels the distance 5 times A. And the other one, different parameterizations in its speed constant is 1, so it travels in time A, travels exactly the same measurement. So basically, it's describing two different particles. One's traveling at speed 5, one's traveling at speed 1. Starting at the same positions. The position, I believe, was 1 minus 2 or something like that. Two numbers we added to it. And so we have different way of parameterize curves, and that was just examples. No, so there's one way we parameterize curve is very important. That is, we start at a point P. Okay. First of all, to parameterize curve, then it depends on a couple of things. First of all, you have to choose the directions, which is a positive direction, which is a negative directions. And the parameterized by arc length, meaning that we set the formula for at any given time equal to, we're going to call the variable s. So when s is equal to 1, so basically the special stopwatch is the s stopwatch. When you stop at s equal to 1, you travel precisely when s stopwatch at 2, you travel precisely at 2 units lengthwise. If a curve is parameterized in these manners, we will say the curve is parameterized by its arc length. Okay. And the parameterization of arc length depends on a couple of things. First of all, it depends on the point you start. So to parameterize a curve of motion by arc length, first, where is the starting point? And second is which direction is the positive direction, which was negative direction. So in general, on the x-axis, the right-hand side is positive and the left-hand side is negative. And on general curve, it's kind of hard to tell, in what sense is left and right. Well, that's a different question. But anyway, roughly that's how it's done. So in this particular case, if I were to start at point 1 minus 2, oops, don't move. The starting point at 1 minus 2 and travel along the curve in this direction, in positive direction, in this case, the line. And then this will be the parameterizations by arc length, starting at the point P with the positive directions as described. I know it's a mouthful. Remember the curve we have that goes five times as fast? Well, suppose I given a parametric curves in terms of time t. Okay, now we're back to beginning, so everything's based on t, and these particular formula indicate exactly the same points as the parametric version we just did, except this one's traveling five times as fast. But the basic question is, given a general formula like that, is it possible for me to obtain the formula in terms of s that parameterized by this formula? Go back to this formula in terms of s. Where s equal to 1, then the length is 1, the length is 2, get a arc length. And there is, I mean, this case is very simple. Basically, you solve the relationship between the arc length of this curve, which is 5 times a versus 5 times s, 5 times a versus when s equal to the a, and solve it back. And here's the algebra for solving the backward. So ds dt, in other words, s is 5 times t, and they can solve for the t, and you can solve s equal to 5 times t. Okay, meaning what? Let me. After you get all these, and meaning that t is equal to s over 5, then you plug the t back into your original equation. What was it? 3t, 3t plus 1 and 4t minus 2. And you put the t s in s back in here, and that's how you get the equation in s, the parameterized by arc length functions. So this is simplest example we can demonstrate that you could do this. In general, of course not. Generally, it's impossible to solve this equation backward after you can't even integrate these things, let alone solve this backward. But theoretically, of course you can do it. So we're going to assume that. So we have this curve that parameterized by arc length. And why do we do that? Oh, because what we mean by curvature, for instance, the most obvious association is if we were to fill the pool as we drive along a curve, say along a mountain zigzags. You go around a corner, sharp corner, you turn, and you fill the pool. The curvature is defined by that pool. I mean, the more sharp it is more harder to turn. That's the acceleration things. The answer is partially correct. Yes, the curvature depends on that pool, but it also depends on the speed you travel. So in order to talk about curvature, we should say everybody drive the same speed. Then you define, at which point you have a bigger pool, so you have a bigger curvature, where on some other turn it's a lot easier to turn. It has a smaller pool outside, centrifugal force, and they have a smaller curvatures. And so, in other words, to find out the curvature, we need the curve to be parameterized by the arc length with speed 1. If we obtain that, assume we have the curve parameterized by its arc length, then the curvature at a point will be the accelerations, the turn, the change in the tangent, the change in the velocity factor at each point. And not only that, we fix every velocity to be 1 in order to be fair. So everybody, so nobody driving faster, so make the pool bigger. So we parameterize by arc length, and then we take the derivative of that, and the second derivative of that, accelerations, and that is going to be the curvatures. Okay. In other words, it's a second derivative, the accelerations of this curve, which is parameterized by the arc length. Okay. Conceptually, this is the geometries. But this, remember, this part was impossible to calculate. I couldn't find the T in terms of the S to plug it back in general. I mean, this is a very theoretical result. Remember, what we are given in the very beginning is a curve, a C of T, and the question is, what is these things of the curvatures? CU curvature at a point P. Okay, in some general parametric equation in T, and we said, we have to do this on the parameterized by arc length first. You have to find this in terms of S first, then you have to find the second derivative of the S. And where the difficulty is, you cannot find the equation between the T and the S to really find the formula for S. Okay, but are there any way to get around it? Yeah, through some algebra. So we went out with the following formula. Okay, and I'm just going to give it to you. Okay, and basically it comes to curvature. This is the curvature formula. Oh, this curvature formula directly in reference to a curve in terms of T, any parametric curve, provided it's increasing, doesn't go back. And you can use this formula in terms of derivative of T. Everything in this formula is derivative of T. Before, the derivative of the curvature was in terms of that strange parameter, not strange, difficult to compute S formula, which we don't know what it is. And the basic proof from here to this formula, you can find in general calculus textbooks. It involves the derivatives between the relationship in S and the C prime of T, and uses product rules. It uses cross products and boom, boom, boom. Then some algebra, then this comes out. You can find this in general in any calculus course. That's the algebraic components of the, yeah. So that's all I'm going to mention about that. Okay. And then the rest of the, you say, 2D curve. How can you define 2D curves in the cross product? Or in this case, you embed 2D curves into a plane with z equals 0 as a 3D curve. Just treat the z component as 0. Then you can talk about cross product. So here are examples going through the calculations and of two different types of spirals in the circle. Okay, and for the circle, the curvature is 1 over the radius if it goes through it. Okay, 1 over r. And for the spiral, and we get the in space, and we get these numbers as the curvatures. And these are the calculations. And that's it. That's all we're going to mention about basically about curvatures. And yes, and it's a simplifying method. That's it. Okay. Bye bye. See you next time. Bye bye.